There we go. Now you can hear me, can't you? Because y'all couldn't hear me before, so let's go ahead and turn this down a little bit so I don't peak as often. There we go. But now you can hear me, can't you? Hey Laura, how you doing? I know I probably lost some folks because y'all thought I was just not talking to you, but you know, here it is. Anyway, so like I was pointing out and couldn't be heard a second ago, I am Aaron Blaze and I teach physics in Houston, Texas. I have so far I've added a few things to this channel that you'll see in this stream, and there we go. See, now I can I can talk to you guys. I probably wasn't talking to you before. Y'all couldn't hear me, could you? So Laura said hi. Somebody else say hi. That'll be fun. Okay, starting in about 75 seconds. And we'll get going. Let me pull up the review that I'll be working from. The physics one from classwork, Unit 1, constant velocity, resources, constant velocity study buddy, way down at the bottom. Okay, I'll be referring to it from time to time. You guys won't be able to see me, but won't be able to see what I'm looking at. But you will be able to hear what I say. One lazy guy, how you doing? Hey everybody. Okay. All right, excellent. 15, 14, 13. So 4. All right. Now, if you could start piling on the questions, that'd be kind of nice, because if it's me talking to myself for only 5 people, this might not last as long as you'd like. So let's go ahead and get started. Okay, so that didn't go quite as I had hoped, but here we go. Let's see if we can't do that transition a little better. There we go. Ah! I don't know why it's not loading. I was such a fan. Ah. Okay, well, like I said, I'll get it all dialed in later as we go along. But okay, so let's start by talking about the very first things on that constant velocity study buddy. Okay, so very first thing, reference point. Now, what is our reference point, and how does it differ from something like the origin? Our reference point just talks about, so let's say reference point. Okay, it doesn't have any units, so that's why it's not listed as having any units. But our reference point is just the point from which we characterize all the rest of our movement. Okay, we just have to pick a place. It's like the very first day when I was discussing where you considered the start of your day. Okay, wherever the start of your day is that you consider, that is your reference point. Everything else is characterized by your relationship to that very first reference point. Okay, so that is what we can say. It's just the point we pick to give all of the rest of our movement context. Okay. Like I was saying, if the more questions that you guys hit me with while we're talking, the better it'll be for everybody. It'll allow my answers to be more responsive to the things you actually want to know. Otherwise, I'm just going to progress slowly through this review. Now, position. So let's go ahead and erase this. Position, on the other hand. There we go. We indicate it with the letter X, and our common unit for it is the meter. Okay? Now, after having picked a reference point or our origin, after having picked an origin, our position is where we are in relation to the origin. Where we are in relation to the origin. Okay. Now, other than the fact that my animation didn't load properly, what do y'all think so far? Has it been? Do you like the changes? All right. So our position is the letter X. We use the letter X to indicate it, and we measure it normally in meters. But it can be measured in any length measurement. It can be kilometers, it can be miles, it can be light years, it can be anything. But it is always in a length. Okay? Because it's telling us how far we are from where we started. Now, frame of reference has a lot to do with our mic has staticky sound to it, but other than that, it's all right. You know what? Let's see if we can't fix that. It's probably too much gain. So, advanced audio properties. Let's go ahead and drop this minus 10. Okay. So close. Boom. There we go. Is that a little bit better? Is that less staticky? I'm probably peaking less often. Actually, let's go ahead and do it one more time and drop it down to minus 15. And this isn't exactly this isn't my best mic. Is that better? Is that better for everybody? I'll go ahead and leave it this way because now I can like kind of talk really loud and it won't peak the mic. So, all right, cool, excellent. Thanks for the update, one lazy guy. Now, frame of reference has a lot to do, is very similar to what we would call our reference point, except it's not just one point from which we consider our origin, but is actually the entire frame of reference. So if you were to say, look at Google Earth, and you wanted to look at a particular restaurant in a particular part of town, you wouldn't zoom out all the way to where you could see all of Texas or the entire United States. You would pick a frame of reference that allowed you to actually see the pieces that you wanted to see, right? You would actually zoom in close enough to see streets that were close to where you wanted to be, and so on and so on. So the frame of reference is just what you pick to make sure that the rest of your analyses can be performed the way you want them to. Okay? What do y'all think of the face cam? Does everybody like the face cam? How's it going? Okay. Let's keep moving. Not all of these are going to be worth talking about, but we'll keep moving along. Distance, displacement, scalar, vector, magnitude. Okay, well these are all good. All right, so let's go ahead and talk about distance, displacement, scalar, and vector. Let's see what else. Magnitude, speed, velocity, average speed, average velocity, instantaneous velocity, relative velocity, mathematical. Okay, so we're not going to talk about all these things, but let's go ahead and add dimensional analysis. Dimensional A. There we go. And that'll be the end of our vocabulary. Let's come back. All right, cool. Okay, everybody can see all those things. Excellent. So, if you like the face cam and liked what I was trying to do with the animations, somebody say hi. Anyway, so distance versus displacement. Okay, so you know what? Let's go ahead and start over here. These words will help give these context. So scalar. Scalar is anything that can be measured just with a number, okay? Measured with number. And I know my handwriting is quite poor, but you know, there it is. Measured with a number, okay? Now, that number that you're measuring your scalars with is actually its magnitude, but we'll talk about that in just a second. but our vectors are measured with a number and a direction. Okay, number and direction. Is that a little bit better? Okay. Yeah, and then it actually fits everything on board. All right, so measured number and vector, or number and direction. That's our vector. Now the magnitude, that is the size of your vector, the length of the arrow, the the reading on your speedometer, whatever. Those are your magnitudes. They are the actual indication of how large or how big the value of it is. All right. So when you stand on a scale, the magnitude of your weight is the reading on the scale. Okay. So when you think, most people think when they hear the word magnitude, they think earthquakes. Well, magnitude of an earthquake is pretty much the same thing. It just tells you how big the earthquake is. Okay, so there we go. Size. So magnitude could be indicated, or it could be defined as the size of a particular scalar or vector. Now, dimensional analysis is a little bit different. That's the thing that we do when we use our units to track down what we're trying to get. Remember in class when I was talking about how if we have kilometers per hour and we're given hours and we're trying to find kilometers, dimensional analysis is trying to figure out what to do with all these units so that we end up getting what we want, because we are analyzing the dimensions. Okay, like that's what it is. So in this case, when we multiply and then say, cancel out our hours and then hold on to our kilometers, that's our dimensional analysis. Another way to do it, a similar thing about dimensional analysis, is let's say we want to turn, let's say 10 hours into some number of weeks. Okay? We need to figure out a couple things. Now, we know that there are 24 hours for every day, right? Like that's just an easy thing to do. So if we do one day over 24 hours, because we need to get rid of the hours and replace it with days, because we know how to do hours. We don't know how many hours go into a week. So if we get rid of these hours, right now, if we just took 10 hours divided by 24 hours in a day, that would tell us how much of a day 10 hours was. And then again, we need to get rid of these days, because again, we didn't know how many hours went into each individual week, but we do know how many days go into a week. So 1 week is 7 days. And again, these days cancel out that day, and so now we have a neat little equation by doing dimensional analysis. By analyzing the dimensions, we know that if we want to turn 10 hours into some number of weeks, we just divide it by 24 and then divide by 7. And we'd end up with however many weeks 10 hours happen to be. Okay, that's dimensional analysis, as well as the whole kilometers per hour multiplied by hours equals kilometers that we did in class. That all counts as dimensional analysis. Okay, I ran a little off the page down here. All right. Okay. There we go. Okay. I know we're down a little bit, but seriously, nobody has any other questions? Where are my questions at? Or like, where's the harassment for the way I look on camera? I don't know. Oh well. Let's continue. But now we can go to talking about our distance, displacement, speed, velocity, average speed, and average velocity. Okay, all those are pretty straightforward and not a lot of trouble. Distance, as we mentioned before, is like total travel. Okay, now that's kind of what it is. It's a lot like the speedometer reading on your car. It only counts up, it never counts down, and you can't like roll any off. even if you were to drive backwards, it wouldn't take the miles off your car. It would just keep counting up because your car is traveling however far that is, even with you headed in reverse. Okay. Now, displacement is very similar, except it's the vector version. Now, we talked about position a second ago, and position is where you are in relation to the origin, just how far you are, 3 meters away, 4 meters away. It's a thing that happens at whatever point you're looking at it. Okay. Now, displacement, or delta x, can be represented as your final position minus your initial position. Now, the reason this is a little different than position is because it's how far you are from your starting point, not where you are in relation to the origin. It's where you are now compared to where you were before. Okay, so your final position subtracting your initial position. So there you go. Now, if you were to say start at 4 and then travel back to 2, in this case, your final position would have been 2, and your initial position would be 4. So your actual change in position would be -2. Like that's how that would work. Okay. I know that's a pretty tiny one, so let's see if we can't get a little closer. See, properties. Yeah, it's supposed to. Yeah, okay. So my computer's just rendering it wrong. But can you see this picture a little more? Can you see this picture a little more clearly? That this is supposed to be a little picture right here. So there we go. Okay. Now, this is one of the things that I added right here, like a closer up version, so we can get a little closer and see. And we'll do that. We'll use that a lot more when we're doing graphs and stuff. But let's go back to the other one. Yeah, so this is a render problem that my thing is doing. Oh well, like I said, we'll keep trying. We'll keep getting better. Oh well. Camera's working. So let's keep going. So speed. Now, speed and velocity are very similar to each other, except that again, one is a scalar, one is a vector. Speed is our distance divided by time. Now, we remember from our discussion 5 seconds ago or whatever, that distance is in fact a scalar. Okay, distance is a scalar, and velocity, or that displacement is a vector. Okay, so our speed is a scalar divided by a scalar. Time is also a scalar. So we take whatever distance we traveled and divide it by however long it took us to get there. So if we drove in a lot of different directions, but over the course of that time we drove 10 miles in 1 hour, then our distance, 10 miles divided by t 1 hour, would give us 10 miles per hour. But our velocity, which is delta x, or displacement over time, is much more this way. Let's say we drove forward 5 miles and then drove backwards 7 miles. So we started off at this point right here, at this reference point that I've just put little dots next to. See, it's just rendering slowly is the problem. All right, so you can see my close-up picture down here with regard to velocity. If we drove forward 5 and backwards 7, we actually ended up 2 from our origin. And if we say that we took 1 hour to cover that distance, then again we have our delta x, which is 2, divided by our time, which is 1. So we'd end up with 2. Instead of the 12 miles we drove, it would only give us credit for 2. Okay? And then these two guys, speed and let's see. Oh well. Man. Okay. So, speed average and velocity average. These you just take your total divided by your total time. Velocity average, total displacement divided by time total. Okay, and just like I talked about in class today with regard to the graphs, an average velocity actually just takes into account the entire thing all at once, as though it were the same throughout the entire time. But that's not actually the case most times. It's usually different throughout that time. So it's pretty rare that you can look at average velocity and use it as though it were the same as velocity that was throughout all the times. That's almost never the case. It's not never the case, but it is usually. Okay, so these are our our vocabulary words. Okay. And like I pointed out, I really need you guys to ask some questions. Like, as much as I enjoy getting extra chances to talk to you guys this way, it's actually not it's actually not my preference that you sit there quietly while I talk. Okay, that's really not my preference. Okay. Visual presenter. Okay. Which one? Okay, OBS 2. All right. Let's see. In task. Okay. Let's see what. Let's see if I can manage anything else. Knock down anything else to see if we can't speed up render times on iCloud. No thanks. What kind of questions will mostly be on the test? Okay, well that's a valid enough question, Catherine. The strict answer is I don't have the test memorized, so I'm not 100% sure exactly what kind of questions will be on the test, but you will be able to expect a fair amount of vocabulary and concept questions like the ones we've been talking about today and in class, and then also the math that we've discussed. But what I'm more interested in is addressing things that you don't understand, because if you understand everything, then it won't matter what kind of questions appear on the test. I turned off a lot of stuff. Let's see if it still, oh well. Let's go back. Okay. That's actually not how that's supposed to go, but there it goes. All right, so I'll pick up a couple of extra things, and then we'll see. Okay. All right, so let's do X versus T and V versus T. Okay, so let's look at those. Let's look at those kinds of. Can you go over the division multiplying thing one more time? Yeah, sure. I will as soon as I do this. Okay, so let's take a look at a position versus time graph, X in meters over time in seconds, and then a velocity versus time graph. Okay, and let's just discuss the features. Okay, so right here is our origin on a position versus time graph. Right here on a velocity versus time graph is in fact just the zero velocity. Okay, the origin does not appear on here. No origin. Okay, no origin appears on a velocity versus time graph. But it does appear on a position versus time graph. Okay. Now, let's say what's happening if we have a line like this. We have a line like this, it means that it started at 0 and is actually headed away from the origin, more and more away from the origin. And as we can see, this line is, at least intended to be, completely straight, which means that it is traveling at a constant velocity. You guys have actually been really good about this. Now, what would the velocity graph look like for this? That would be a constant velocity, which would be like that, and we could tell that it has a positive slope, so it would be on the positive side. Now, let's draw two versions of the same graph. So that one and that one. And let's see if there would be any difference between those two graphs. And they're supposed to be the same length and same slope and everything. I know they don't look quite that way, but let's assume that they are. Okay? And let's talk about what kind of graph it would have. Now, the slopes on both of these are 0, and slope in a position versus time graph is its velocity. Both of these lines are intended to be straight, so they are constant velocities, and they have a negative slope. So here we go. Now, if these lines did have the same slope, they would both have the same velocity versus time graph. They would have the same velocity versus time graph. Because, like I said, the origin and your relation to the origin does not appear anywhere on the velocity versus time graph. So it doesn't matter that one guy starts way up here and one starts way down here. It only matters that their velocities are the same. So that's what you'd get. Okay. But so we already did one in class, the little pyramid looking one. So let's talk about what are the features of a velocity versus time graph. Who can remind me, what does it mean if your velocity is on this side on the positive side of the graph? Which direction are you headed? Can anybody answer that for me? I know I got close to 14 people out there for at least a little bit. Who can tell me which direction we're headed if we? Okay, so forward. That's a good. Okay, lazy guy. That's actually a better answer. So we heard one forward and one away. The away is actually the most true. Now, on the positive side of a velocity versus time graph, you are headed away from the origin. Okay, that's what it is. And I know, like when we had these over here, you can argue that they would be a little bit different. You're right, but Pogs, I have questions. But anyway, so what does that mean? What direction does that mean you were headed if you were on the negative side of the velocity versus time graph? And there are no answers, sadly. That's not true. There's almost always answers. Either way, that was off topic. Towards the origin. There we go. There we go. So if you have a positive velocity, you're headed away from the origin. If you have a negative velocity, you're headed towards the origin. I know that's not quite right if you have a position graph that goes along with it, but trust me on that one. Okay. All right. So we've done a couple of those position versus and velocity versus time graphs. Y'all really want that face? Y'all really want that face cam on my gaming videos, because I think we'll be over 5 viewers as of this. But either way, let's take a look at what's coming up next. Okay, so can you do the division multiplying thing one more time? Okay. Now, part of dimensional analysis and one of the... Hey! How you doing, Sean? Nice to see you here. Thanks for the follow. Hope this is going to be valuable for you. Okay. Now, let's answer Nina's question of can you go over the division multiplying thing one more time. I assume what you mean, Nina, and correct me if I'm wrong, that you're referring to our dimensional analysis thing that I was using instead of talking about the specific equations. Is that true? If not, let me know. Okay. So the example we used in class was two cars going different speeds. I know this is different than the one we did in class. I'm doing that on purpose. Okay. And let's say they both drive, let's just go ahead and say 2 hours again. Makes the math easier. Okay, 2 hours, right? Now, we want to know how far each one goes. Okay. Now, there's a couple things that I want to talk about how to get good grades on tests. And I know, knowing the math is definitely one of the easiest ways to, like just being good at all the material is the best way to be good at math. But it's not the only way. And besides, everybody makes mistakes, and part of being good at things is being able to identify when you have made a mistake first. Okay, so somebody out there, I mean, Nina, if you keep feeling like typing, that'd be fantastic. But I know there's 9 other people watching us, so let's see if we can't get some more participation. Which car, Ganon the Evil. Okay, well, in a second, I can get to a question about that, but I know something about numerical mathematics. You'd have to ask your question about whether or not, for me to know whether or not I know what you need to know. But anyway, so we're talking about our 2 cars right here. Now, right off the bat, how can we tell which car is going to go further? Who can tell me which car is going to go further? A or B?
I'll just go ahead and talk with Meatwad in the meantime. Yeah, okay, so there we go. Yeah, so car B will go further than car A, right? Now, that is important because when we do our math, we need to keep in mind that car B should go further. So when we do our math, we need to make sure that is what we get.
Or it's not going to make any sense when we give our answers. Okay, so for some reason we say that A is actually going to go further, then that we know we made a mistake. Okay, we need to keep track of that. So let's go ahead and start to do our math. Now, the way we did it in class was I took everything we knew and put it on the left side of an equation. Ooh, it is raining outside. So I knew my velocity, kilometers over hours, and I knew my time in hours, and I knew that what we were looking for was our kilometers. So we needed kilometers over here. Now, because I've had a long time with this material, have these equations tattooed on my brain, right in there. But you guys are just learning, and I want you guys to understand these better than just memorize them, okay? And part of that is going to be, sort of understanding why we do the math in the order that we do. Okay, so we have this right here, and I want to know what operator, plus, minus, multiply, divide, I want to know what goes on in there, what goes there, in order to give us this. Okay, now, it doesn't seem like it immediately, but you can move these units around and cancel them out as though they were numbers. They do move around that way. So we need to cancel out these 2 hours. And we remember from our algebra that every number or anything is just the thing divided by 1. So we have an hours in a denominator and we have an hours in a numerator. And in order to get those to cancel out, we need to multiply them together. That cancels that guy, that cancels that guy, and that leaves us with our kilometers. And that means that all we have left is our kilometers. And so to do the rest of this math, we just need to repeat it. So we just needed to multiply our velocity multiply it by our time. So 50 km per hour multiplied by 2 hours. Get rid of both those h's, get rid of both those hours, and we are left with 50 times 2, or 100 kilometers. And let's repeat ourselves. 75 kilometers over hours multiplied by 2 hours. Hours cancels, and we have 150. And so, does this match what we said we would get before? Does this agree with what we get before? Does car B actually drive further? Car B does drive further. So what you guys had said was probably going to be the key is what happened. Okay, so there we go. Now, hold on a second. Let's see. Let's get a little bit closer and see this math real quick. Ah, man, why is this taking so long to render? Oh well. Trust me, it is super cool. All right. Okay. Now, so we did see that 150 kilometers car B drove further. Okay. Now, the slightly more complicated one is the second one we did in class. So let's knock this stuff off and say, all right. Okay. Meh, whatever. Okay, so let's say now that they drive 225 kilometers. Okay, I was trying to figure out some number that I could do in my head. Now, let's go back. See how cool that would be if this thing were rendering fast enough. Oh well. Okay, so we're trying to drive 225 kilometers at 50 kilometers an hour and 75 kilometers an hour. So just like last time, which one is going to take longer? We're looking for time here. Which one is going to take longer to get further? Letter A or letter B? Exactly. Okay, so we got a good vote. Letter A. Can I get another? Who agrees with him? Precious. Okay. Am I this rubber-faced in real life? I can't tell. Okay, so we have two. Catherine. Okay, A. Okay, so everybody agrees. The slower car is going to take longer. Now again, let's keep that in mind to make sure that that is in fact what we experience when we do our calculations. Okay, so hello. All right, but like we said before, we have our kilometers over here and our kilometers per hour. And again, let's just go ahead and draw that just because. And we need hours over here. Okay, this one's a little trickier because it uses division rather than multiplication. Multiplication is easier. But so, and I've already given away the ghost, but the operator we need to put in there is the divide. Hold on a second, let me move this around. Let me put it up here so I can work a little more freely. Equals hours. Now, okay, so how does that work out? Now, follow me a little bit, and this is a little bit mathy, but if you practice it, you'll get the rhythm of it, and it'll work out. So, dividing something by something is like multiplying by its reciprocal. So, if I were to say 12 divided by 4, that would be equal to 12 multiplied by 1/4, right? And both of those would equal 3. Okay? Does everybody get that? So our kilometers divided by kilometers per hour Okay, it's not a dumb question. Stop saying stuff like that. And I'll get to it in just a second. So, when we have this, it is equal to kilometers multiplied by hours divided by kilometers. Okay? And now, you can start to see it over here. Now, these kilometers cancel out, and we are left with hours. Okay? That's why we had this divider in here. Okay? Now, and let's see, what happens if we do it the other way around? Okay, so what happens if we do it the other way around? So if we had kilometers per hour and then divided it by kilometers. Okay, so dang, that's the same thing you said over the. Okay, I mean, okay. If we do that, this kilometer will cancel out that kilometer, and what we are left with instead is 1 over hours. Okay? So, like you can see, it matters which direction you do these in. Okay, so let's talk a little more in depth. How do we know when to divide and when to multiply? A little like what Nina is saying, you guys are still new enough with this material that it is unlikely that you'll recognize as quickly as I do what needs to be done exactly when. Okay, and it really, really, really is not a smart or dumb or anything guy. Point. You guys are just new at this. Okay. So just the way like somebody who's playing basketball knows when to use a crossover dribble or to step back and take a shot versus drive to the net, all these things come from experience, okay? And you will gain the experience as you go on. And that's even why I've started teaching these things as the whole this and then this equals hours. So what do we need to put there? Like I'm trying to emphasize the fact that you don't really need to know right off the bat what you need to do, that you can figure it out just from the parts that you were given. So that's a very good question, Catherine. And my guess is that for most of this course you will probably at least feel as though you're not sure what you should be doing. But if you follow your units around the way I'm saying here, and don't forget this 12 divided by 4, 12 times 4 thing is just for example. It doesn't pertain to our question. But if you follow your units around this way, it will make it easier to figure out what you should be doing. It's not this class is intended, and I really think it should be, a lot less memorization than you might think. Okay? Like I really hope that when you leave this course, you know how to figure out some of the math stuff. And this is a big part of it right here, figuring out these kinds of things. Okay? Does that help? Something about the back of a target and a guy. Yeah, I mean, I did say all that, but okay. I need a haircut. All right, so let's go ahead and continue with this right here. We need to know what our time is, okay? And we figured out that we need to divide our kilometers, divide it by our kilometers per hour, okay? So we have 225 km divided by, and actually, you know what? Let's write this out a little more explicitly. So, I'm going to strike off some of this stuff so I can stay on frame. Okay. So we have 225 kilometers divided by 50 kilometers per hour. And that gives us So 225 divided by 50 is 4.5. That K and that K cancel out, and this moves up here, so 4.5 hours. That's our time for the 50 kilometers per hour. Next one is 225 kilometers divided by 75 kilometers per hour. That K and that K cancel out, and that H moves up there, and we end up with 3 hours. Hey, there comes back that 3. So, did we think that car A was going to take longer? Because that's what we got. And again, everybody makes arithmetic errors. I make arithmetic errors. You guys have seen me make arithmetic errors. But by knowing what to expect, by knowing that we should get car A gets a higher time, a longer time, we can be pretty sure that since we got what we wanted, that this is pretty close to the right answer. Okay? Whew. All right. So, Catherine, Nina, does all of this make more sense than it did a second ago? Yeah, see how long it takes to render out? Man. Catherine, Nina, did that all work for you guys? I can do another one. Okay. Excellent. Well, in that case, I'm going to leave this up for just a second so you can copy down some stuff, and I'm going to find another problem to do. Okay. Okay. Okay, so in just a second, I'm going to do one more problem, and that'll bring me up to the hour that I was intending. I can stay for one or two more questions if you guys ask one or two more questions. Right now it's a little quieter in here than I expected. Who here is quiet just because they're anxious? Feel free to say hello. It will make things less scary if you talk. Ooh. Got a quick drink. Okay, let's move on. Now, let's do one more thing. Okay. Angela, dang it. Thank you. Hey, Jada. Welcome. Nice to meet you. Thanks for joining at the very, very end. All right, so let's go ahead and look at a couple of these and see if we can't figure out our displacement. These are velocity versus time graphs. Okay, and let's see if we can't figure out our displacement. Let's just make it easy. 5, 10, 0. Now, why do y'all keep apologizing? Goodness, stop apologizing. You didn't do anything wrong. Okay. Okay, 5, 10, and let's say this is 3. Okay? Like, am I intimidating? Why do people keep apologizing to me? Is it because you're afraid I might cry? Alright, either way. Let's go back to this guy. Man! I need a better computer. Or I need to, like, do something. I don't know. Speed it up or something. Yeah. Basket fire. I don't even know what I'm going to do with all my Easter eggs with this basket fire. Alright, so. Let us look at these two right here. They're both velocity versus time graphs. And what I want to do is figure out how much displacement is represented in both. Okay? Who's got a guess? How much displacement do you think is set up in here? Do y'all like the funny voices? So you like the funny voices. Alright. Okay, well either way, let's go ahead. So, when you're calculating, we're trying to figure out how much displacement is represented by each one of these graphs. Okay? So, the way we do that is by calculating the area between the line and the x-axis. Okay? Normally we say area under the curve, but it's not exactly under. Okay, well we'll find out in just a second. It's not exactly under, especially when we're talking on the negative side of the graphs. Okay? So, what we're going to do is we're going to figure out what the area of each one of these boxes in, this stuff is. We're going to add them together, and then that'll be our displacement for that part of the graph. Okay? So this right here, these two things are rectangles, and I know they look like squares, but they're not drawn to scale, and every square is in fact a rectangle. Okay, so let's find out if Angela is correct. I like the guesses. Okay, so this right here, and we're just adding up all of our area, delta x. This right here is a rectangle, so it's going to be base times height. And then this is a rectangle, so it's again going to be base times height. Now the base of this rectangle is 5. Its height, right there, is 2. Plus, our base right here from 5 to 10 is again 5. But our height is -2. Okay, so 5 times 2 is 10. 5 times -2 is -10. So for this one right here, this one is in fact 0. Okay, and that one's a little bit easy to guess just because these two things look the same and they're right next to each other. But this one might be a little bit different, a little more difficult. Same kind of calculation, but we have a triangle, and the area of a triangle is 1/2 the base times the height, and then here's our rectangle down here plus a base times a height. So 1/2, our base is from 0 to 5, so again 5, and then our height is 3. So 1/2 of 15 plus our base is again 5, but our height is -2. So 7.5, or 15 times 1/2 plus -10. What's 7.5 minus 10? It's off the thing. Okay, let's move it up. There we go. 7.5 minus 10 is -2.5. Okay? Does everybody see how I got that? Ask me a question. I got one correct guess and a couple of incorrect guesses. Okay. When solving for the displacement on a graph, we solve for the area. That is true when we have what kind of graphs? What kind of graphs am I working from right here? What kind of graphs am I working from? What kind of graphs do I got? Velocity versus time graphs. On a velocity versus time graph, your displacement is calculated by calculating the area under the curve. And when I say area under the curve, what I mean is the area between the line and the x-axis, just like we had over here. On a velocity versus time graph, you can calculate the displacement that way. Yeah, exactly. Thank you. Now there are shapes. Are we specifically going to need to know that for the test, or is this just a way of explaining? Okay, you might need to know it for the test just to do this area under the curve thing. You won't need to graph or interpret a velocity that changes. Okay? And it's a good way to check your work, like with letter F on the worksheet from earlier this week, or from Friday of last week. You would have been able to check your displacement calculation with doing this method on your velocity versus time graph. Okay, So this specifically refers to velocity versus time. You can't do this on a position versus time graph. So there are the occasional differences. Okay. I have time for one more question. Okay, let's pull this up so you guys can see it a little more close. Ah! What do I do? It's still covered up by some of this stuff. Okay. All right, excellent. Thank you guys very, very much for paying attention to this. We did work through the entirety of my constant velocity study buddy, and we've done lots and lots of problems. Okay, now let's talk for just a little bit. Okay, so this class is obviously anxiety producing for many of you, and even though we say I'm good at physics every single day, free hundo if I go to the open house. Can we go over a problem about position graph? Okay. Open house is at 6:30. Okay. Well, okay. Before I give my little speech, can we go over a problem about a position graph? Okay. So. Okay. It's an oldie but a goodie. Okay. Okay, so let's call this A, B, C, D, and E, and then we will graph its velocity. We're not going to do any calculations. We're just going to talk generically. Okay. So what on a position versus time graph gives us our velocity? What about a position versus time graph is the velocity? I bet somebody's typing it right now. It is the slope. The slope of a graph on a position versus, there we go. The slope on a position versus time graph is the velocity. Now, who can tell me right away where on this graph there are two places that the slope is equal to 0? Where are they? Give me the letters. There's two of them. B and D. Excellent. B and D are at 0. So let's just go ahead and break this down into A, B, C, D, and E. I know it's not drawn to scale, but whatever. Don't at me. So for B and D, we have 0 slope, right? That's this part and this part. So they are just straight at 0. Done. Right there. Excellent. Good job, Jada, Angela, Nina. Excellent. Okay, so now what? Where do we have a positive velocity? We have two places with positive velocity. Who's got them for me? A and E, right? Now, we have A and E and both is positive, and I kind of intended for this one to look steeper. So that means its slope is bigger. So let's go ahead and draw. And since these are both straight lines, we're going to say they have a constant velocity. But like we said, A has a positive one, and E has a more positive one. Okay? And then B, or C, down here, from here to here, appears to have the biggest slope, although it's negative. So again, flat line for section C. So there we go. everything that's going into that. And if we had more data, we could calculate the value of these at y, but we don't need it, okay? Because if you were to do a multiple choice test and you were to draw this graph to help yourself understand what you're doing, there's little chance that there would be a whole bunch of these that would look like this. You would probably draw one, it would probably look like one of the answers, and you would move on. You wouldn't even have to do the math for it. Okay. Again, let's pull up. This is, okay. I don't know. We'll do something different. All right. All right. Is there a dumpster fire emote? Because that's what I'm feeling a little bit. Anyway, so has everybody got this right here and figured this one out? I hope. Good. All right, let's do this now. Okay. I actually do have to get going, but it was nice talking to you. But now I know we are working through with this mantra, and I know that most of you have not really sort of bought into it yet. You still think it's just a goofy thing that we say, and that it doesn't actually pertain to you. Now, you are starting to get this, and truthfully, you are understanding this at least as well, if not better, than most of my other classes over the course of 7 years. You are no worse off than anyone else has been at your level, okay? And that includes me, what must have been 6,500, 7,000 years ago. This was new to me as well, okay? And I talk very fast, and I talk very loud, and I talk very confidently because I want you guys to believe that I know what I'm talking about. And I do, but that is not a thing that happened instantly, okay? I'm making this grand statement, this sort of locker room pep talk, because this is still early enough that if you do start to believe in yourselves, you have a long time to get good at this. You have a long time to get good grades in this class and to feel good. And because I heard some of you talk about wanting to be doctors and stuff like that, and you can be those things if you believe that you are good at physics and good at your other classes. You have just as much chance and as much opportunity to do that as anybody. And I think all of you can. Okay, so like I said, I actually have to cut very short just to get to the open house and to make sure that I have enough time to eat and to relax a little bit. It's been a long 8 days now with Navy over the weekend. So you guys are good at physics, and you knew more answers to this than I've seen in most of my other years before. So you guys have a good chance. Get a good night's rest, and you'll kick butt tomorrow, and we'll be back to playing games on Tuesday. Okay? So let's say goodbye. Thank you very much for joining me. And if you come to open house, come by and see me. If not, I'll talk to some of your parents, and if not, I'll see you in class. See you later.